All right, welcome linear algebra students to our first online lecture. This is the first online lecture I've ever made in my entire life. So we'll see how this goes. Hopefully it won't be too rough, and hopefully we'll be able to make sense of this all together over the next couple weeks. So the topic we're going to talk about today is section 4.4 on similarity and diagonalization. So those are two $10 words we're going to need to try and unpack a little bit and try and make sense of. So the first idea we're going to talk about is similarity. So suppose I give you two matrices, A and B, and they happen to be matrices of the same size, two square matrices. Well, if you can find a third matrix P that allows you to relate your two matrices in this way, so that allows you to write B is equal to P times A times P inverse. Well, if you can find a third matrix P that makes this equation work, then we say that the matrix A is similar to the matrix B. Okay? And if that's the case, well, then the matrix B will also be similar to the matrix A. And so we would just say that A and B are two similar matrices. So that's going to be kind of the topic we're going to focus in on today. But what geometrically does it mean for two matrices to be similar? This is kind of a weird equation to try and impose, especially if it's the first time you've seen it. And so you might be wondering, what does this mean geometrically? Well, I'm going to post a little example online sometime in the next day or so that'll kind of work through this with you. And if you're interested in this, you can read through that example and it'll give you a little bit better idea. But I'll just give you a quick overview right now what's going on. So suppose we start off with a vector x. Well, we could multiply the vector x by the matrix A, and that would give us some vector A times x. Okay, so you can think of this as being a linear transformation that takes the vector x and transforms it into the vector A times x. Now, if you'll remember from section 3.5, we talked about coordinate bases, or we talked about bases. Now, a basis is a set of vectors which is both linearly independent and spans Rn. So in this case, let's say our basis is denoted by this fancy looking curly C. One of the things we talked about in section 3.5 was that if you have a basis, that allows you to write every single vector in Rn in a unique way as a coordinate vector. And this is the notation we used. So using our basis, we can take the vector x and we can express it as a coordinate vector with respect to that basis. Now we can also do the exact same thing with the vector A times x. We can express it in terms of this coordinate system or this coordinate basis. And the question you might ask is, how are these two vectors here related? In other words, when we express our vector x in coordinates and we express our vector A times x in coordinates, how do you get from one to the other? Well, your first guess might be we just multiply by the matrix A. But it turns out that's not correct. The matrix A is no longer going to work once you've converted everything to coordinates. But there will be some matrix B that does work, that allows you to take the coordinate vector of x and convert it into the coordinate vector of A times x. And the question is well, how are the matrices A and B related to each other? And the answer is that A and B are going to be similar to one another. They're going to be similar matrices. So long story short, if you have two matrices that are similar to one another, you should think of them as both describing the same linear transformation, but just possibly in terms of different coordinate systems. Okay? And that's about the depth of what we'll need to understand about these things. So we won't go too much more into depth, except for in a very special case, which will come up in a minute. There are a few facts that we might want to keep in mind as we go ahead. So the first and probably most important is that if A and B are similar matrices, then they'll always have the same characteristic polynomial, and they'll always have the same eigenvalues. So two matrices that are similar will always have the same characteristic polynomial and the same eigenvalues. And that's going to be an important fact. So let's keep that kind of packed away in the back of our heads. It's actually not too hard to prove, so maybe I'll prove that right now. You guys are all hankering for a proof, I know that. It's been a rough week for some of us, right? And nothing calms you down like a nice proof. So let's go ahead and do that. So let's assume that A and B are similar matrices, okay? Or in other words, they can be related by an equation of this form. Well, let's go ahead and let's prove that the characteristic polynomial of A is the same as the characteristic polynomial of B. Okay. So first of all, we're going to write down the characteristic polynomial of A. That's just by definition the determinant of A minus lambda I. Now we can take the matrix A and we can replace it with P times B times P inverse. Okay, because we're assuming that they're similar to each other. And now we can do another bit of algebraic tomfoolery, and we can replace this identity matrix by P times P inverse. All right. Now, hopefully that's clear that this is just the same as the identity, and this P times B times P inverse is just the same as A, because we assumed that they were similar. All right. Well, why did we do this? Well, notice on the one hand, right here, I have a P on the left and I have a P on the left here. So I can factor a P out on the left-hand side. And likewise, I have a P inverse here and a P inverse here, and they're both on the right-hand side, so I can factor them both out on the right-hand side. And what's left in the middle is B minus lambda I. Okay? Now we're all very astute, and whenever we see a product of matrices inside a determinant, the first thing we think to do is we think of splitting up that determinant. So we're going to split this up as determinant of P times the determinant of B minus lambda I times the determinant of P inverse. Oops, that's a B. I want a P inverse. Okay. Now, also because we're clever individuals, we remember that the determinant of P inverse is actually the same thing as 1 over the determinant of P. So this thing, if we take advantage of that fact, gives us the determinant of P times the determinant of B minus lambda I times 1 over the determinant of P. And now, we're no fools. We know that whenever you have a determinant P and a 1 over determinant P, they cancel each other out. And so we're just left with the determinant of B minus lambda I. Okay, but wait, what is that? This is the characteristic polynomial of B. This is the characteristic polynomial of A. What we've done is we've shown that they have to be equal to each other. So because we assumed that A and B were similar, it turns out that they have the same characteristic polynomial. And because the eigenvalues of the eigenvalues of a matrix are just the roots of the characteristic polynomial, this also tells us that the eigenvalues are going to be the same, and they're going to show up with the same multiplicity. So for example, if the eigenvalue 1 shows up twice for the matrix A, it's also going to show up twice with respect to the matrix B. Okay? So this is a useful fact. Now, unfortunately, it doesn't quite characterize what it means to be similar. So what do I mean by this? Well, for example, here are two matrices. Let's compute their characteristic polynomials, and let's then see if they're similar. Well, if you want to compute the characteristic polynomial of the first matrix, that's just the identity matrix. So that's determinant of I minus lambda I. So that's the determinant of 1 minus lambda, 0, 0, 1 minus lambda. And when we use our 2 by 2 determinant formula, this is 1 minus lambda squared. Okay. On the other hand, we can do the exact same thing for the matrix A. We can compute its characteristic polynomial. And so this will be 1 minus lambda, 1, 0, 1 minus lambda. And when we compute its determinant, we get 1 minus lambda squared. So notice these two matrices have the same characteristic polynomial. What does that tell me? Does that tell me that they have to be similar? Well, actually, no. So sadly, the answer to that question is no. And you can see that these two matrices are not going to be similar to each other pretty easily. For example, suppose that the matrix A was indeed similar to the matrix I. Okay? Well, if that were the case, that would mean that there's an invertible matrix that allows me to relate these two things as so. But now the identity matrix is special. I can just multiply it by P inverse and it kind of disappears and just leaves me with a P times P inverse. And then when I multiply P times P inverse together, I just get the identity. So in other words, if the matrix A were similar to the matrix I, then in fact that means it has to be equal to the matrix I. And And we can clearly see that the matrix A and the matrix I are not equal to each other. In other words, what we've proved down here with this little observation is that the only matrix that is similar to the identity matrix is the identity matrix itself. And so in fact, since this is not equal to the identity, there's no way that it can be similar to the identity. So this is kind of a little bit of a warning, because these two matrices had the same characteristic polynomial, they had the same eigenvalues, but in fact, they're not similar to one another. So if you want to check whether two matrices are similar, it's not enough just to check that they have the same characteristic polynomial. So that's our first warning. Just because two matrices have the same characteristic polynomial does not imply that they are similar to one another. Our second warning is that similarity is not the same thing as row equivalence. So you may have two matrices that can be related to one another through row operations. Those two matrices aren't going to be similar to each other in most cases. In fact, when you do row operations, a lot of the time what happens is that the eigenvalues themselves will be changing in the matrix. And so because similar matrices have to have the same eigenvalues, if you're doing row operations and you're changing the eigenvalues, there's no way that those two matrices, even though they may be row equivalent, there's no way that they're going to be similar to each other. So similarity is a relationship that you can use to sort of compare two matrices, but it's not the same relationship as row equivalence. So please keep that in mind. All right, now we're going to be interested in this property of similarity, particularly in the case where one of the two matrices we're looking at is a diagonal matrix. Okay, so that brings us to the following definition. A matrix A is said to be diagonalizable if it is similar to a diagonal matrix D. In other words, A is diagonalizable if you can find an invertible matrix P so that A is equal to P times D times P inverse, where D is a diagonal matrix. Okay? So we're still talking about this idea of two matrices being similar, but the only thing we're doing now is that we're restricting to the case where one of those two matrices is a diagonal matrix. So the first question we might ask is, if a matrix is diagonal, then what does that tell you about this matrix D inside of there? What does that matrix D have to look like? Well, if A is equal to P times some diagonal matrix D, I'm going to write it as, say, A, B, and C. And I'm going to put a 0, 0, 0. I'm going to make it diagonal, right? That's what we want to do. All right. So if we have a matrix A, and if it's similar to a diagonal matrix D, what does that tell me about these numbers here? Well, notice that those numbers there, A, B, and C, those are going to be the eigenvalues of the matrix D. Okay? So those are the eigenvalues of the matrix D. On the other hand, notice that two similar matrices have to have the same eigenvalues. So in other words, whatever the eigenvalues of the matrix D are, those will be the same thing as the eigenvalues of the matrix A. Okay? So in other words, these values A, B, and C that we wrote down there, well, really, they have to be the eigenvalues of the matrix A. So lambda 1, lambda 2, and lambda 3. Okay? So the answer to our question, if A is diagonalizable, then the matrix D is the diagonal matrix whose entries along the diagonal are just the eigenvalues of the original matrix A. Okay? So hopefully that makes sense. So in other words, if A is similar to a diagonal matrix D, we know exactly what the diagonal matrix D has to look like. Okay? So we know what this diagonal matrix D is. The question is how do we figure out what the P matrix is? Well, we'll get to that in a bit. But let's look at an example here first. So here we have a matrix A, we have a diagonal matrix D, and we have an invertible matrix P. Let's verify that the matrix A is indeed diagonalizable by showing that A is equal to P times D times P inverse. All right, well, to do this, we need to, first of all, I guess the first step is we want to multiply these three things together. We need to figure out first what P inverse is. So let's go ahead and compute that. P inverse is equal to 1 over the determinant of P. So in this case, that's going to be 1 times negative 5 minus negative 2 times 2. So that's negative 5 plus 4. And then if you remember, we're going to swap the diagonal entry. So this will be -5 and 1. And then we're going to change the sign of everything that's not on the diagonal. So if I'm not mistaken, I think that's what we should get. And if we look at this term out here, that's just 1 over -1. So when we multiply that in, I think we should get 5, 2, -2, and -1. Okay? All right. Good so far. So now, in order to check that indeed A is diagonalizable, all we're going to do is we're going to take the matrix A, and we're going to check that when we multiply it out, when we multiply P, so this is 1 times 1, 2, -2, -5, times D, 2, 0, 0, 1, times P inverse. So what we need to do is we just need to check that this actually gives us what we want it to do, what we want it to give us. And in fact, so I'll let you verify this on your own. But what you'll see is if you multiply these three matrices out on the right-hand side, you will see that they do indeed equal A. Okay? So we didn't actually tell you anything about how to find the matrix P. You kind of know where the matrix D had to come from because you know that the 2 and the 1 essentially have to be the eigenvalues of the matrix A. So you know where D came from in some sense, but we don't know where P came from. We'll come back to that in a minute. But what's one kind of question we might ask you about this? Well, suppose we're in this setup here. One thing you can do with diagonalizable matrices is you can use them to compute matrix powers very easily. So suppose we wanted to compute the value of a to the power of 10. Okay? Well, that's going to be a really complicated thing, right? Because you're going to be taking the matrix A and you're going to multiply it by itself 10 times, right? And that's kind of a messy thing to do. But what you might notice is that if we multiply A times A times A, and say we do this 10 times, well, we have a fact that we can use, and the fact is that A is equal to P d P inverse, okay? So if we take P d P inverse and we use it to replace every time we see A, we get P d P inverse times P d P inverse times P d P inverse all the way up to P d P inverse, okay? And if you're going to drop the brackets, notice what you're going to see is you're going to see a P inverse and a P right next to each other, and then a P inverse and a P right next to each other, and another P inverse and P right next to each other. And all of these P inverse P's are going to cancel each other out. And the only thing you're going to be left with is a P on the left-hand side, a D. Now the D's don't cancel each other out, so we get D to the power of 10, and then we get P inverse here. Now why is that an advantage? Well, the nice thing about diagonal matrices is it's really easy to compute high powers of them. Okay? So in other words, because D is a diagonal matrix, D to the power of 10 is easy to find. You just have to take the things on the diagonal and raise them to the power of 10. So you get 2 to the power of 10 and 1 to the power of 10. And now, because it's so easy to raise that matrix D to a high power, we've simplified our life greatly. And if we plug our matrix P and our matrix P inverse back in, what we're going to see is we're going to get 5, 1, 1, 6, 2, 0, 4, 6, negative 1, 0, 2, 3, 0, and negative 4, 0, 9, 1. Okay? So the advantage of doing this was that it's really hard to raise a matrix to a high power, especially if there's, entries in every single spot. But if you're just raising a diagonal matrix to a high power, all of a sudden that computation becomes very easy. You just have to raise the values on the diagonal to that power, and then you just have to multiply by the P and the P inverse, and you get your answer. Okay, so that's one way we can use diagonalizable matrices to sort of simplify computations. All right, let's come back to this question about determining when a matrix is diagonalizable, because not every matrix is going to be diagonalizable. Then we also want to know, if we know that our matrix is diagonalizable, how do we figure out what the matrix P is? The following theorem is going to basically give it to us. Now, instead of reading through the theorem, it's worded maybe a little awkwardly, so I just want to give you the gist of it. The idea is that if you want to know whether your matrix is diagonalizable, what you've got to do is you've got to try and find as many linearly independent eigenvectors as you can. So if your matrix is n by n, if you can find n linearly independent eigenvectors, then your matrix is going to be diagonalizable. If you can't find n linearly independent eigenvectors, then your matrix is not diagonalizable. So that gives us a way to check whether our matrix is diagonalizable or not. Once we know that our matrix is diagonalizable, then the way that we find the matrix P is we just take those n linearly independent eigenvectors that we found and we put them in as the columns of the matrix P. And so that's basically the procedure for both determining whether a matrix is diagonalizable, also once you've figured out whether it's diagonalizable, finding what the matrix P is going to look like. So let's look at an example here. Let's try and diagonalize this matrix if we can. So we're going to try the following steps. The first is that we're going to find the eigenvalues of the matrix A. The second step is we're going to look for n linearly independent eigenvectors of A, if we can find them. They may or may not exist. If they don't exist, if we can't find n linearly independent eigenvectors, then we're stuck and our matrix is not diagonalizable. On the other hand, if we do find n linearly independent eigenvectors, what we do is we take those vectors and we put them in as the columns of a matrix, which we call P, and that's going to give us our P matrix. So that tells us how to find the P matrix, and then we already know how to find the D matrix from before. We just take the eigenvalues of the matrix A, we plug them in as the entries along the diagonal in D. And that's going to give us both our P matrix and our D matrix, but of course, there's lots of places to make mistakes, so another important step is that we should check that, in fact, A equals PD P inverse. So on a test, you can always go through these, the steps, and then when you got your final answer, you can always check to make sure that it works. Then there's always one final step we need to take care of, and that is to wash our hands. We don't know where any of these eigenvectors have been, so it's always a good idea when handling new eigenvectors to make sure that you wash your hands afterwards for good hygiene and health. All right, so let's try this example here. We're going to work through these steps right here. We're going to find the eigenvalues, we're going to find the eigenvectors, and once we've done that, we're going to build our matrix P and our matrix D. So let's go ahead and let's do that. So step one. We're going to find the eigenvalues of the matrix A. So to do that, we're going to find our characteristic polynomial first, so the determinant of A minus lambda I. So that's going to be 7 minus lambda minus 6, 0, 4, minus 3 minus lambda, 0, minus 6, 6, and 1 minus lambda. All right, now fortunately, I was in a good mood when I made this question, and I gave you a column with most all zeros. So let's do cofactor expansion along that column. When we compute the determinant, that's going to give us 1 minus lambda. And then on the inside, we're going to take the determinant of this piece right here. And remember, this here is in a positive spot in the checkerboard pattern, so it gets a plus sign. And then I multiply it by the determinant of this piece right here. So that's going to be 7 minus lambda times minus 3 minus lambda minus 6 times 4. And if we simplify that a little bit, I'm going to do it in my head because I'm quite skilled at these sorts of things. I'm not looking off pre-written notes. Just doing it all in my head. Lambda squared minus 4 lambda plus 3. And we can factor that second part there. It gives us 1 minus lambda times lambda minus 1 times lambda minus 3. Okay, and so therefore our eigenvalues are going to be the roots of that polynomial. So we're going to be, say, lambda 1 is equal to 1, lambda 2 is equal to 1, and lambda 3 is equal to 3. All right? Now, I just want to point something out because this might be handy on a test. Notice my characteristic polynomial is a cubic. And so ultimately what I want to do is I want to get it down to factored form. Now, when I was computing my characteristic polynomial, I basically got one of the factors for free because of this cofactor expansion. Now, I want to kind of leave that factor out. I didn't want to multiply that factor through because if I did, then I'd have a cubic that I have to factor, and that'd be a lot of work. So I kind of hung tight there and left this guy on the outside here, and then I just computed this characteristic polynomial, and that's the only thing I needed to factor in the end. So in other words, if you don't have to multiply everything out, it's a good idea not to because you'll save yourself some work factoring in the end. Of course, that's not always going to be possible, but sometimes it will be. We found our eigenvalues. The next step is to find our linearly independent eigenvectors. So let's give ourselves a new page to work on there. So this is step 2. We're going to find linearly independent eigenvectors. All right, so let's start off with our lambda 1. Let's start off with our eigenvalue of 1. So lambda 1 is equal to lambda 2 is equal to 1. That's the one we're going to work on first. So of course we take a minus I. So this gives us, what does our matrix look like? It'll be if we look back to the previous slide, that's going to give us a 6, minus 6, 0, 4, minus 4, 0, and minus 6, 6, 0. And so when we row reduce this, it row reduces quite nicely, and we just get 1, minus 1, 0, 0, 0, 0, 0, 0, 0. And what does this tell us? It tells us that x is equal to y, and z is a free variable. Okay, so remember, this first row, we should think of this as giving us an equation, x minus y equals 0, and then that's where we get the x is equal to y, and then we get that z is a free variable. So if we take the vector x, y, z, we can replace the x with a y, so we get y, y, z. And then if we split this up like we always do, we get 1, 1, 0 times y plus z times 0, 0, 1. Okay. And so what this means is it means that we found a basis for our eigenspace. And that basis is given by 1, 1, 0, 0, 0, 1. Okay? Now, the important thing here is that we found two vectors. And that's actually going to be a good thing, as we'll see in a minute. So then we're going to do the same thing for lambda 3, which is equal to 3. We get a minus 3 times the identity, which is going to be equal to 4 minus 6, 0, 4 minus 6, 0, and minus 6, 6, minus 2. If we row reduce this like we did above, we're going to get 1, 0, 1, 0, 1, 2/3, 0, 0, 0. Okay. And this tells me then that x is equal to minus z, y is equal to minus 2/3 z, and z is free again. And so therefore we take x, y, z. We're going to replace the x with negative z. We'll replace the y with minus 2/3 z. And when we pull out the z, we get minus 1, minus 2/3, and 1. And so a basis for our eigenspace here is going to be -1, -2/3, and 1. Okay? All right. So it's at this point, I just want to actually emphasize, notice that we really haven't been doing anything that we haven't done already. So all we've done so far is we found the eigenvalues, and then we found a basis for each eigenspace. Okay? So this is something we did in section 4.3, and we even saw that in 4.1. The question is, though, now the question we can answer is whether or not our matrix is diagonalizable. Well, our matrix started out as being a 3x3 matrix. So in order for it to be diagonalizable, we need to find 3 linearly independent eigenvectors. Well, notice the 2 eigenvectors we found here are linearly independent. And if we throw in this third one, it will also be linearly independent because it comes from a different eigenspace. So what we've done is we found 3 linearly independent eigenvectors, and because our matrix is 3x3, that's all we need to do. We found we can definitively say that our matrix A is diagonalizable now. So we can proceed along our merry ways, and we can complete the problem. So step 3 was to construct the matrix P from the eigenvectors we just found. So our matrix P is going to be 1, 1, 0. That was the first eigenvector we found. 0, 0, 1 is the second eigenvector we found. And then -1, -2/3, 1 is the third eigenvector we found. So that's going to be our P matrix. Our step 4 is going to be to construct the D matrix from the eigenvalues. And so the eigenvalues we found were 1, 1, and 3. So we write down a diagonal matrix with 1, 1, and 3 along the diagonal, and that'll be our D matrix. Now people always ask, does it matter the order that I write the eigenvalues down in? And the answer to that is no, it doesn't matter the order. But whatever the order you choose for the eigenvalues here, you need to stick with that same order for the matrix P. Okay, so because we did 1, 1, and 3, we need to make sure that we do a 1 eigenvector first, a 1 eigenvector first, and then a 3 eigenvector. Okay, so you just need to make sure that whatever the order you did with P, that's the same as the order you did with D. Then our final step in that list is to check that A equals PDP inverse, and I will leave that for you to do at home. I will also leave the step 6 for you to do at home, and that is to wash your hands. Okay, but that does it. So we can see that diagonalizing a matrix is really no more work than what we've been doing already. Just finding eigenvalues, finding eigenvectors, and then just building the matrix D and building the matrix P from them. All right. Now we can proceed and we can do the same thing for any square matrix that we give you. So for example, I could give you a 2x2 matrix and I could ask the exact same question. In the interest of time, just so these lectures don't get too long, maybe I'll skip this example here. But if you look at the annotated version of the notes, which I've posted on Learning Suite, you'll be able to walk through those steps. And it'll be an easier example than the one we just did. So if you understood that first example, you can walk through this example here, and it should be no more difficult than that first example we did. Let's skip to this example here, though. This is maybe a little bit more interesting. So let's diagonalize this matrix here, if possible. So we're going to go through our steps. I'm not going to write down the explicit steps, but we're going to start off by finding the eigenvalues of this matrix here. So we're going to look at the determinant of A minus lambda I. So that's going to be the determinant of 1 minus lambda, 1, 0, 0, 1 minus lambda, 1, and 0, 0, 1 minus lambda. Now this is nice because it's an upper triangular matrix. It's really easy to compute the determinant. So we just get 1 minus lambda cubed. And so therefore, the eigenvalues are all just equal to 1. So lambda 1 is equal to 1, lambda 2 is equal to 1, and lambda 3 is equal to 1. Okay? So now let's go ahead and let's find our eigenvectors. So if we do lambda, if we look for our eigenvectors for this eigenvalue, we're going to start off by doing A minus 1 times the identity, which is just the matrix 0, 1, 0, 0, 0, 1, 0, 0, 0. And that all already happens to be row reduced for us. So what this tells us is it tells us that y is equal to 0, z is equal to 0, and x is free. And hence, if we start off with x, y, z, if we replace y and z with 0, we get x, 0, 0. And so therefore, a basis for the lambda equals 1 eigenspace is just this vector here, okay? Now this is going to be a problem. Remember, in order to diagonalize my matrix, I need to get 3 linearly independent eigenvectors. All that this procedure has done for me is produce 1 linearly independent eigenvector. Now, of course, I could take this eigenvector and I could multiply by any non-zero scalar, and that would give me another eigenvector with eigenvalue 1. But those eigenvectors that I find in this way would not be linearly independent. They'd all be linearly dependent. So in fact, what this procedure shows is that it only produced 1 vector when in reality I needed 3, and therefore my matrix is not diagonalizable. Okay. So in order for A to be diagonalizable in this situation, I would have needed to get 3 eigenvectors out of this procedure. And since I only got 1, that tells me that my matrix is not diagonalizable. So this illustrates the type of problem you can run into when trying to diagonalize a matrix. Essentially, you just end up not having enough linearly independent eigenvectors to build the matrix P, and therefore you can't diagonalize it. So, well, there are certain situations in which you're never going to run into this problem. For example, if I give you a matrix with n distinct eigenvalues, then that matrix will always be diagonalizable. Why is that the case? Well, for example, if I give you this matrix here, notice my eigenvalues are going to be 1, 2, and 3. Because it's an upper triangular matrix, that's easy to see. Now, because I don't get any eigenvalues with multiplicity greater than 1, notice I'm guaranteed to get at least 1 eigenvector here. I'm guaranteed to get an eigenvector here, and I'm guaranteed to get an eigenvector here. Since those 3 eigenvectors come from different eigenvalues, they're all going to be linearly independent. Therefore, I'm going to be able to get 3 linearly independent eigenvectors, and therefore this matrix will be diagonalizable. Okay, so because I didn't have any eigenvalues that showed up more than once, my matrix has to be diagonalizable, and that's a fact you can take to the bank. All right. Now you do have to be careful. Just because a matrix doesn't have n distinct eigenvalues doesn't mean that it won't be diagonalizable. For example, if you remember this matrix we saw in the first example, it had eigenvalues 1, 1, and 3, and even though the eigenvalue 1 showed up twice, when we found the eigenvectors, we found 2 eigenvectors to go along with that. So even though it had an eigenvalue of multiplicity greater than 1, we were still able to diagonalize it. And essentially, it came down to the fact that it showed up twice as an eigenvalue, and we happened to find 2 eigenvectors, 2 linearly independent eigenvectors when we did that procedure. So that's basically the idea of what this is going to come down to. All right, so if you remember from a couple classes ago, the algebraic multiplicity of an eigenvalue is the number of times that it shows up as a root of the characteristic polynomial. So it's the number of times it shows up as an eigenvalue. The geometric multiplicity of an eigenvalue is the dimension of its eigenspace. Or in other words, it's the number of eigenvectors you get, the number of linearly independent eigenvectors you get when you when you look for eigenvectors. So the only situation in which a matrix will fail to be diagonalizable is if you have an eigenvalue whose algebraic multiplicity is greater than its geometric multiplicity. In other words, maybe the eigenvalue 1 shows up a bunch of times. Maybe it shows up 3 times in your list of eigenvalues. Well, what that means is if I want my matrix to be diagonalizable, I'd better hope that I get 3 linearly independent eigenvectors from this eigenvalue. If I only get 2 or I only get 1, then I know that my matrix will not be diagonalizable. Okay? So that's what this theorem here says. Let A be an n by n matrix. Well, the geometric multiplicity of an eigenvalue is always less than or equal to its algebraic multiplicity. The matrix is going to be diagonalizable if and only if, when you add up all the geometric multiplicities, they add up to the number n. Okay? In other words, if I have a 3 by 3 matrix, I need to look at the number of eigenvectors I find, and I'd better get 3 linearly independent eigenvectors. If I have a 7 by 7 matrix, I need to add up all the eigenvectors I find, and I better get 7 linearly independent eigenvectors. The third thing is that if A is diagonalizable, then combining, if you take all these eigenvectors and you put them together, these linearly independent eigenvectors, and you put them together, then they're going to give you a basis for all of Rn. And the fourth fact is that hand washing and social distancing is the best way to slow the spread of the coronavirus. So let's restate this theorem a little bit differently. Okay? What this theorem is telling me is that the geometric multiplicity of an eigenvalue is always less than or equal to the algebraic multiplicity. And the matrix is going to be diagonalizable if and only if the geometric multiplicity of lambda is equal to the algebraic multiplicity of lambda for every single eigenvalue. If you find a single eigenvalue whose geometric multiplicity is less than the algebraic multiplicity, then you're not going to be able to diagonalize it. All right, so just as one last example, suppose we have a 5 by 5 matrix with 3 distinct eigenvalues. Suppose that one of the eigenspaces has dimension 3. The question is this matrix diagonalizable? Well, let's think about this. So we have 3 distinct eigenvalues, lambda 1, lambda 2, and lambda 3. Now, because our matrix is 5 by 5, we know that at least one of these eigenvalues has to show up with algebraic multiplicity greater than 1. Okay? But on the other hand, we're told that one of the eigenspaces has dimension 3. So for example, suppose that lambda 1 has a 3-dimensional eigenspace. That means that we can find 3 linearly independent eigenvectors that belong to this eigenspace here. Okay, so they belong to the eigenspace for lambda 1. On the other hand, we know that for lambda 2 and lambda 3, we know that we will always get at least one linearly independent eigenvector from each of those. So suppose for lambda 2 we get an eigenvector w, and for lambda 3 we get an eigenvector u. Okay? Well, because we got 5 eigenvectors, and we know that these 3 eigenvectors are linearly independent because we chose them to be so. We know that these ones are linearly independent because they come from different eigenspaces. What we found is that we have 5 linearly independent eigenvectors, and since it's a 5 by 5 matrix, that's all we need to find in order to diagonalize our matrix. Okay? All right, that does it for section 4.4 for us. That also finishes off chapter 4. The next chapter we'll be going into will be chapter 5, but we will have a review day in between because we have a midterm coming up. I hope this lecture has been okay for you. Hope you're all safe and healthy. If you enjoyed this video, make sure to hit like and subscribe. We'll see you next time.